Good morning, everyone. My name is Kelly Kane, and I'm the Marketing Manager for EandM. Thank you for attending our webinar today, Taking the Pain Out of PID. After the webinar this morning, we will be doing a short Q&A. Please type any questions or comments into the Q&A box, the chat box, or email us at eandmwebinar@eandm.com. Now I'd like to introduce your presenter for today's webinar. Your first presenter is Bill Hintz. Bill is EandM's Siemens Product Manager and works with customers to design new applications for Siemens products. And your second presenter will be Jim Willis. Jim is an engineering manager for Max Process Equipment. Max is a manufacturer of urethane processing equipment. So let me go ahead and turn it over to Bill. Good morning, Bill.
Good morning, Kelly, and thank you. Welcome to another of our Friday webinars. This one today, as Kelly mentioned, is Taking the Pain Out of PID. What we're going to be using today is, I'm going to go over a couple of things first, and we'll pass it over to Jim to let him show you how he has used PID and some of the hardware and software, and then I'll go over what we're going to use, and then we'll talk a little bit about PID in general. What we have today is actually Siemens' next generation of configuration software. We're going to be using TIA Portal. And TIA Portal is a package that allows us to encompass all of the different parts of an automation project. For example, we can have PLCs and HMIs and networking and remote I/O and everything all in the same project. And it gives us some significant advantages in that we have a common database for all of the different devices there. And one of the things that I really like is the global library concept. So once I've configured something in TIA, I don't have to do it again. And that's real nice. I mean, for example, if I use an analog input card that had first couple channels with 0 to 10 volts, a couple more with 4 to 20, maybe a temperature sensor on another channel, and that's a template for what I'm going to be using again in the future. I just grab that and drop it into my library, and then the next time I start a project, I pull that in. So the idea of the design advantages of TIA Portal is that we don't have to duplicate efforts, and we're not starting from scratch every time. The next step is for commissioning. TIA gives us lots of tools for being able to actually quickly commission something, and Jim's going to talk a little bit about that today. What we're showing here is kind of an oscilloscope thing, and what it does is it's actually taking all the different components of a project and actually putting all their signals on one screen. So I can see the relative motion that we're actually monitoring up here in the upper area, and then see the results of pushing buttons and seeing sensors and that kind of thing, which is a very handy tool to be able to see everything that's going on in a new project. And lastly, what I'm showing here is the maintenance side of TIA. And maintenance is important. You know, I got a question the other day about the mean time between failure of a PLC. And I looked it up, and it was 80.1 years for a S7317, I think it was. It's a pretty amazing number. What it kind of brings to focus is that the issues with maintenance and repair are much more being focused on the mean time to repair something rather than the mean time of failure. So in other words, if somebody runs a forklift over a conduit and suddenly we've got a machine down situation, what TIA gives us is, since we have this common database and the diagnostics are throughout the project, we can actually have the capability of somebody out on the plant floor, rather than having to go grab a laptop and plug in and with TIA Portal and so forth. All these diagnostics show up everywhere on the system. So that gives us, we can lower the technical requirements of somebody to be able to fix a machine and get it back up running quickly. Okay, so using TIA, the hardware today actually that we're going to be talking about in the PID loops is the S7-1200. 1200 has standard Profinet on all the processors. A nice feature of it we're showing here in the middle is anybody that's done field service work with PLCs realize that you go online with a PLC, you upload the code, and it comes up, it's got no names, no comments, no explanation as to what you're looking at, other than you just have to kind of reverse engineer what's out there in the field. TIA gives us this symbol names and comments. All the project information is actually in the PLC when we do a download, so that's kind of neat as well. Now, the next guy on the block is the 1500. He's actually the newest release from Siemens. It's been out almost 2 years now, so it's established in the market. What it gives us, actually, this nice big screen on the front there is real handy for doing what I had mentioned with the diagnostics. We can actually see a diagnostic log of everything that's happened, and with things like intermittent faults and loose wires and that kind of thing, it's invaluable to be able to just see time-stamped what happened, why the process is down, or why it went down, but now it's running and you're standing there looking at a running machine, but you know it's going to break as soon as you leave the building. So all these different features are built into the diagnostics automatically, and we just needed a way to see it. So the 1500 gives that right there on the front screen. It also gives us remote, all the other parts of the project as well. So if we've got a remote I/O node that's got a fault on it, we can see that from the PLC screen as well. Okay, so that's the hardware that we're going to be talking about using today. Let's talk a little bit about PID and how the PID algorithm is integrated into TIA. PID historically has been a fairly difficult implementation process, and one of the pains of PID has been exactly that, trying to figure out where all the different parameters go and trying to, well, you spend a lot of time in manuals to get PID running. TIA has actually fixed a lot of that, and let's take a look on how that it does that in a moment, but at first, let's just talk a little bit about PID. PID is, in its simplest terms, is just it has a set point. So we're going to do a closed loop control of something. It can be a heater, it could be a flow, it can be temperature, it can be a lot of different things that we can control with closed loop PID. And what PID utilizes is a set point. We have a process variable, which is a feedback from the process, and then we have an output. So if I look over here on the screen at the right, well, let's say this is an air compressor, for example, and we want to get up to 100 PSI. We put in a set point of 100 PSI, we start out at 0, and then actually as the output comes on, we're going to vary the speed of a motor, for example, the compressor motor. It actually brings us up into set point. Now, how does PID handle that? Really, it uses set point and process variable and subtracts the PV, the process variable, from the set point to give us what's called error. And once we have that error, which at the startup would be 100 because we have a set point of 100 and a pressure of 0, then we apply these P, I, and D math algorithms to that error, and they add them all together, and that gives us the output. Now, in simplest terms, the P value is it's just a proportional output to what the error is. So if I had a proportional output of an error that was 100 at the startup, it's just going to pass 100 out to the output. So if we just used a pure P value and we looked at the way that the response would happen with a purely P system, we would see that as we go up, our error goes down. So as that error declines, the actual amount of output from the P variable is going to go down. So eventually what happens is we kind of level out at an area that we have an offset from our set point because we've actually lowered the error to the point where the P can't get the rest of it. And that's where we bring integral in. Integral actually looks at the amount of error over time. And so what it does is it just slices up in time increments the amount of error and adds that to the output. So if we have an error in here, and excuse me trying to write with a mouse here, it just every time increment it's going to add that to the output. And eventually with a PI type of an algorithm, we're going to be able to bring this up and our error should go away. We have a nice little system that looks pretty much like that. So we should have a nice startup. It comes up to set point, levels out, and a PI algorithm can work for a lot of applications. You hear PID because D is a very handy term to actually add to a lot of loops because it solves a couple of problems that just PI doesn't. D is actually a measurement of the rate of change of the error. So actually, if we look at when this starts ramping up there, the derivative is actually looking at how quickly that error is changing. And it would fight our output. So in other words, what it can do is it can save us from some of the things that we see with just a PI loop, and one of which would be overshoot. So if this PI loop without D were allowed to overshoot, then that'll cause a lot of problems with a lot of applications. For example, if we were maintaining the level in a sewage tank, you don't want to overshoot and actually spill sewage. It also happens with other applications like temperature control, where if you go over temperature, then you may have a problem. And I think Jim's going to talk about a little bit about that in a minute. So when we add D, and actually it will look at the rate of change there and actually fight that and level us back out again. Another possible use of derivative would be, let's say once again we're looking at an air compressor, and this air compressor is controlling a variable compressed motor, and the end user of this air is going to be a paint booth. So the guy's out there painting cars, and we've got this tuned in real nice for the amount of air that you would use to paint a car. And then somebody someplace actually grabs an air hose, goes out in front of the building and sprays a bunch of leaves off the front driveway. What's the result going to be of that? We're going to see a drop here. So it's going to suddenly drop very quickly because we're using a huge amount of air that we were never tuned in for just the paint booth part of this. Derivative will see that error happen and actually fight that rate of change, turn up the air compressor, and D can be very handy on applications like that where we have everything tuned in very nicely for P and I, but then there's a change to the system. D is very helpful with that. So that's PID. How do we get these numbers for PI and D? And that's actually the tuning of a loop. And let's talk about how we might do that. One of the old-time methods is called Ziegler-Nichols, and this is kind of an auto-tuning algorithm. It comes from the 40s, and really all you do is you turn off the I and D function, and you turn up the proportional of the p-value until the loop oscillates. And once it's oscillating like this, we can look at two things. We know the number of the p-value that we've turned it up to get the oscillation. We also know the distance between the peaks here, so we actually look at the period of the oscillation. And using those numbers, we can actually come up with a kind of shoot from the hip number of how to tune a loop. So for the p-value, we're going to go at about a half, 0.45 of that oscillating value. And for the I value, we just look at that period of time that it took to oscillate and divide that by 1.2. So for a PI controller, that's how you would tune it using the Ziegler-Nichols. For PID, we would actually change the numbers a little bit. We go to a 0.6 for P. We divide the I is going to be the period divided by 2, and then the adding in of the derivative at P divided by 8. So that's kind of a heuristic way of tuning loops. And heuristic means essentially it's a rule of thumb or an educated guess. Where we get into trouble with these type of things is that you're just still not totally sure that this is the absolute best way to tune that loop. And so what Siemens has done is they've got tuning parameters and so forth, but there's really two different pains in getting a loop running. The first one is actually just configuring the actual configuration of the algorithm so that it will work. And what they do is instead of having to pull out the manual constantly is we just go ahead and we grab things like we're going to do a temperature loop and we just fill in the blanks with the pull down menus. And the second part of PID is that this auto-tune function makes you real nervous if you've used auto-tune, you think you've got your loop tuned in and everything's fine, and then you decide on a whim, well, let's just turn it off and on again and try the auto-tune again. and then it gives you a different set of variables. That'll make you a little nervous. One of the things that you really want to avoid, like I said, was overshoot with loops, and there can oftentimes be some very bad consequences to that. So let's talk to somebody here about somebody who does PID for a living, and with that, I'm going to hand this over to Jim Willis, who's been doing this for some time. Here you go, Jim.
All right, thanks, Bill. Jim, I'm passing the presenter role over to you right now, so you should be able to show your screen.
Good morning.
Good morning, Jim.
Okay. How does
there
that
we go.
look?
We can see your screen. Perfect. Thank you.
Very good. Thank you, Kelly. And good morning, everyone. Great job, Bill. Always a hard act to follow. I'm Jim Willis, Engineering Manager for Max Process Equipment. We are located in Healdsburg, California. I have a question for you guys. Hello?
Yeah, we can hear you just fine, Jim.
Okay. Someone was talking. So any of you guys go out and, to Ace or Home Depot and buy some epoxy? So when you get home, you take out the little tubes, turn the pack over, squirt out a little bit of A and a little bit of B, take the popsicle stick and stir. How much A and how much B to use? Well, something like 50-50. Polyurethane is not epoxy, but the principles are the same. High-quality polyurethane parts require precise ratios of A to B. If you have too little of the B, you'll get a sticky mess. And if you get too much, you'll have brittle material. So our customers demand performance, including precise ratios of A to B. And, very important, they require reliability. So those loops that provide that precise ratio control must be stable. So flow rates are a prime candidate for PID closed loop control. Our spec and our customers demand ratios, our material be dispensed on ratio to within 1 part per thousand. And we partnered with EandM and Siemens since about 1995. Actually, Bill's been there since the beginning to provide our customers with high performance and reliable control systems. This is an example of one of our larger machines that we shipped last year. It has 2 large tanks, looks like maybe 400 and 225 gallons, with 8 pumps and four sets of mixtures. And the application required that those 4 mixers be used simultaneously and that they stay on ratio while the total output of the dispenser was slowly changed. So it was a challenging application. So what's polyurethane used for? Here are some typical polyurethane products. Interestingly enough, it started with golf balls and skateboard wheels. So some of the high-end golf balls are polyurethane skins. Protective eyewear. Lower left-hand side is a polishing disc. So the abrasive is embedded in the polyurethane. Foam earplugs. And another interesting application is undersea cables. So the agenda today, we're going to take you through the process of building and optimizing PID control on a polyurethane processor using Siemens TIA portal. And it's going to include using organizational blocks, specifically cyclical interrupts. We're going to need a sensor object, an actuator object, and the TIA portal PID object. And then finally, show the results from tuning an actual liquid dispenser. As Bill showed us earlier, PID control requires that we have a sensor, and that provides the PV. I call it process value, by the way. I think it's actually process variable. A set point, an actuator. In this particular case, it will be a pump drive. A set point, and the PID controller. So it really simplifies to four objects. Jump into a little bit of the implementation. As I said, we're going to use OBs to organizational blocks to contain the sensors, PID controllers, and the set point managers. And those cyclical interrupts are run at varying rates. The sensors, we're going to run at 10 times per second. PID controller, we're going to run that at about 3 times per second. And the set point manager about once per second. And the reason for this is the sensor time rate depends on 3 things: the response time of the sensor and its associated data acquisition rate, the response time of the process, and the desired level of smoothing or filtering. And by using cyclical interrupts, especially for the sensors, we're guaranteed that we have periodic timing of the data acquisition. And so that means later on, if you want, you can use that data for things like Fourier frequency analysis. It's always a good idea to have a prototype when you're developing PLC code. So here's my sensor prototype. It's about 25 years old. It's been put to good use. It has features of a readout, a way to calibrate, you see the 0 and span, an adjustable low-pass filter, a name, some engineering units, and a way to provide trending. By the way, this box is still in use, and the current project is to replace it. This is the sensor faceplate for, well, it's universal. It's for all sensors, but it's going to take the place of my prototype sensor. It provides for converting the raw data from the A to D, let's say, into the process variable, and turning that raw data into engineering units, and also to provide the filtering. So calibration, filtering. And you can also see inputs for engineering units and the name of the sensor. In this case, B2 line temperature. As I said, the sensors are going to be contained in an OB, cyclical interrupt, with a timing of 10 times per second. And all the sensors are very similar in their characteristics, and all the sensors go into that OB. So the sensors just run, and those PVs are available for any other program block that needs them. The secondary purpose of the sensor object is to provide that filtering. And we chose exponentially weighted moving average, EWMA. EWMA is the mathematical equivalent of an RC low-pass filter. So it's the same thing that you saw on the front of that big box. Those knobs on the big box change the RC low-pass filter. And of course, we need a drive. This drive is probably the simplest form of interface to a variable frequency drive that is used on the pump motor, and it has some inputs of let's see, set points, speed from the drive, speed to the drive, and then some control words passed back and status passed back and forth. In this particular case, we used a Siemens G120C variable speed drive to control the pump motor speed. And PIA Portal allowed us to commission the drive from the same project that we used to develop the PLC program. I'll touch on that later on. And this is the PID object that is supplied by TIA Portal. It has inputs, set point, and process variable, and it has output, pump speed. So there are the 4 things that I need. It also provides access to the Autotune feature, which is done in the upper left-hand corner of the, see if I can use this. Does that work? Yeah, right here. It's one of those 2 buttons. And when you press those, then you get the Autotune, and I called it faceplate. Autotune proceeds by, the blue lines are the output of the PID controller, and the next color that looks sort of like a sine wave is the response of the system to that set point change. So it proceeds by going, in this particular case, the set point was mid-range, 50%, and it applies about 80-something% to the output, waits until the process value crosses that set point, and then it goes to another set point. And you can, if you look closely, you can see it also varies the time between those square waves. And in a span of 2 minutes, it converged on an answer. And I had now a fully tuned, optimized PID loop. So here's some results. Again, this is actual data taken on a urethane processor here in the plant in Healdsburg. The fundamental test for performance is to ask for a step change in the set point. In this particular case, went from 10% of maximum to 90% of maximum. And you see up at the top of the graph, it says lambda equal 1. That means there's no filtering on the sensors. And it's just taking the raw sensor data and putting it into the PID controller. If I have a mistuned loop, and I'm illustrating this by changing the filtering to lambda of 0.05 when it was tuned at 0.3. So I now have, I've slowed down the response of the, by applying the low-pass filtering, I've slowed down the response of the sensors, and so the loop is no longer tuned properly for those sensors. And as a result, you see overshoot. Also, when you're testing the performance of the loop, you need to go from minimum to maximum range, typically 10 to 90%. And then from 90 back to 10%, and see it both going up and coming back down. The same setup with lambda at 0.05, simply retuned, and it's back to behaving nicely. But if you look closely, especially compared with the first one, it's a little bit slower in its response. So that's a consequence of, if you apply more low-pass filtering to the sensors, then it's going to take longer for the loop to stabilize. Maybe more accurate control. It depends on your application. So Bill brought up a very important point. How do we know that we have a stable PID controller and that it would be stable over any of the set point values that we anticipate? So we expect it to run on a set point range of 0 to 90%. And so what I did here was I repeated the auto-tune feature, and I plotted in here the P values and the I values and the D values for those multiple runs. And across the x-axis is the set point. I tuned it around, most often I tuned it around 50%, but I also tuned it at the two extremes. And what I found was the P values and the I values and the D values were pretty stable across that range. They only deviated a little bit at the low end. So I can look at this and say, you know, this thing gets the same answer time and time again. So it's probably pretty good parameters, good performance across the range, except maybe at the lowest end of the range. And if you think about it, this was a pump, closed loop control with a pump and a flow meter. And if you think about that, when you excuse me, slow the pumps down, you have very little flow going through the system. Excuse me. It is more difficult to control. But I would say probably this would certainly be stable above 20% good PID values, and maybe a little sluggish at the low end. You see, at the end of the day, you're going to have to pick one value for PID, and it's got to work across this range. And so by looking at this, I can say these PID values work from 20% to 90%, and maybe a little sluggish at the low end. So this gives me confidence that I have a reliable tuning. Most of the control loops used, at least here, tend to be PI only. Folks were afraid of using the D term. It wasn't fully understood, and it seemed to cause some problems. But actually, D is a good thing. And this is the same hardware with, you can select the PID controller, you can select the PI only. And so this is an optimized PID controller for that same flow loop. And what you see, it doesn't make set point, decides it's gone too far, and does a little oscillation, and then very slowly makes its way up to the set point. This would be out of spec. No customer would want to wait 1 minute to get its flow rates back on ratio. So in conclusion, we have hopefully demonstrated optimal PID parameters, acceptable performance, and acceptable reliability over a range of at least 20 to 90%. And did I mention that I did all this from my desk? The equipment was actually in another part of the building, and all of this was done over Profinet. So what that means is a well-designed and implemented system like those available from Siemens TIA Portal 1200s and 1500s with Profinet can be optimized from anywhere in the world, provided, and you guys probably know how difficult this is, you have an internet connection to the machine. And the result is our customers are pleased with our performance and reliability, and that makes me a happy camper. So thank you for your participation. I'll turn it back to Kelly and Bill for questions.
Okay, great.
Well, thank you,
Jim. Yeah, go ahead, Bill. I think you see a few questions that have come in.
Yeah, I saw a couple come in I thought we'd throw out there. First one is, how many PID loops can a processor run? I'll go ahead and grab that one. PID loops, the number you can run are really determined by the time base that we're using for PID. So in other words, we have to execute all of these PID loops within a interrupt time. So if we've got a 100 millisecond interrupt, we have to execute everything in that 100 millisecond, or else we actually run over ourselves. The rule of thumb for the 1200 has been 16, and that's just on a very basic PID loop calculation. The 1500, I don't have a rule of thumb number, but it's a lot more, and it's based on execution time. The processor's in the 1500, it goes all the way up to the 1518, which is a nanosecond execution time processor, which probably means we could run a multitude of loops. I guess hopefully that answers it for you. Next question. I keep hearing about bias in PID. What is bias? Jim, I'll take that if you want, or if you want to grab that, it's either one.
Please go ahead, Bill.
Okay. PID, usually when we talk about PID, there's two different flavors. There's what's called velocity PID, and there's positioning PID. So velocity would be if we're doing a PID loop that's going to control the speed of a motor. That's a velocity loop. And what that means is when you actually reach set point, you want to maintain the output to keep that motor spinning. Positioning is different. Positioning means you turn up the motor to get your actuator out from point A, and when it reaches point B, you turn the motor off. The difference between those two algorithms is what's called bias, and bias just means that we're going to continue, the integral keeps adding to bias during the ramp-up time for a for a velocity loop. And so when we get to set point, it just maintains that same amount that it took to get there. The positioning loop has no bias value, so it actually, when it gets there, it's done and turns off the output. Hope that answers. The last one was, can you use digital pulses instead of analog outputs? Yeah, one of the configuration things is called PWM, that's pulse width modulation. And so instead of using an analog output to a VFD or whatever your actuator is, we could use a pulse width modulation. Just means we're using a digital output, and we have a time base. So the time base could be 1 second or 10 seconds. And if the loop output is 50%, and our time base is 10 seconds, that just means that the output's on for 5 seconds and off for 5 seconds. It's a lot less, well, I wouldn't say, it's less expensive way of doing PID. Analog outputs are more expensive than digital ones. It also allows us to use things like solid state relays for heat temperature control. That's typically how temperature control works. Analog can be more precise, but digital pulse width modulation is used a whole bunch. I do have a couple of other questions. Yeah.
Yeah. This is Jim. I just want to point out, I think you were part of the implementation years ago. We use pulse width modulation to open and close solenoids that take hot glycol heater material, working fluid, out of our heaters and put them into our recirculating lines. And in your example, our time base is 10 seconds, and so if we know that we need 30% duty cycle, we'll open that solenoid for 3 seconds. So it's a way to control slower devices that have slower or much longer time constants.
Great, thanks, Tim. There's one other question here. I'm going to answer by email. It's going to get a little involved there. One more thing, follow up on the bias. So the question is about bias and transitioning from manual to automatic mode. It's called bumpless transfer, and this is where we do use bias. And actually, what we're doing is we're getting into the innards of the PID algorithm, and although we don't need to do that with TIA, we still have access to them. So what happens with bumpless transfer, that just means that we're going to start up something in manual mode. Maybe we have a speed control and we just want to turn it up to get a motor up to the speed we want, and then we hit automatic and it goes over to PID. Well, if you don't use bumpless transfer, what would happen is PID would start with no built-up bias in it, so it would droop way down, look for an error, and then come back up and find its set point again. By using the bias value in pumpless transfer, we just transfer the output that we're set at for the manual mode into bias, and then when we go into the automatic mode, it takes off from exactly where we were in manual, and that's called bumpless transfer. So hope that answers that one. That's all the questions I'm seeing right now.
Okay, great. Thanks, Bill. And thanks, Jen. That was a very informative and a great webinar. And a recording of this webinar will be available on our YouTube channel as well as our website a little bit later this afternoon. So if you do think of any questions after the webinar, feel free to email us at EandMwebinar@EandM.com. But that does wrap up our webinar for today. Thank you, everyone, for joining, and have a great weekend.
Thanks, all.